This is the third and the final presentation in Chapter 9 over hypothesis testing. We're going to look at the three different test statistics. The three cases are when we're testing the mean and we know sigma, we're testing the mean, we don't know sigma, and then the third case is when we're testing the proportion. Now, no matter which test statistic it is, you're basically going to follow the same process. First, you've got to figure out what your null and your alternate hypotheses are, and then you get the level of significance. You calculate whatever statistical information that you need and plug it into the formula and come up with the computed value of the test statistic. Then if you're going to proceed with the p-value, you do it one way. If you're going to proceed with the critical value, it's a little bit different. But no matter which way you do it, you should come up with the same result. I'm assuming that EMS stands for Emergency Medical Services. Now, they have the response time for a random sample of 40 emergencies. The mean of that sample was 13.25 minutes. That's your X-bar value. The population standard deviation is given as 3.2 minutes. So we know what sigma is. So we're going to be able to use the test statistic for testing the mean where we know sigma. Now we're using a 0.05 level of significance, and we want to see whether or not that service goal of 12 minutes or less is being achieved. Now, to determine what the null is and what the alternate is, think about where you're going to take action. Are we going to do anything if our service goal is being met? Well, we end up with a number that's less than 12 minutes. That's fine. The only thing that's going to cause us to take action in this situation is if we have an average value that's bigger than 12 minutes. If it's significantly bigger than 12 minutes, well, we need to do something about this. We don't want to take a lot of time to respond to an emergency. So we're going to be trying to find evidence that that average value is bigger than 12 minutes. This one's going to be an upper tail test. So the alternative hypothesis is that mu is greater than 12. We're going to have a one-tail, upper tail test. Under the null, it's just the opposite. We're going to assume that mu is less than or equal to. The problem specified a 0.05 level of significance. Now we can take the statistical information and plug it into the formula for this type of problem, x bar minus mu divided by sigma over the square root of n, and come up with the computed value of the test statistic. In this case, it turns out to be 2.47. Now, what we do next depends on whether you're using the p-value approach or whether you're doing the critical value approach. Now, this illustration is for the p-value approach. You take your computed value, the 2.47. This is an upper tail test, so we want the probability to the right of that point. You can go to the z-table and look up the 2.47, and the value that's on the interior of the table, the probability value, is the probability that's to the left of 2.47. That number is the 0.9932. Now if you subtract that from 1, you're going to get the probability to the right of 2.47. And that's the p-value for an upper tail test. So the p-value for this problem is 0.0068. Now that's quite a bit smaller than alpha. Alpha is 0.05. So it tells you to reject the null. But you go to the table, you look up the 0.9932, subtract it from 1 to get the p-value, and then just compare it to alpha. Now we're rejecting the null, so we have sufficient evidence to show that the Metro EMS, that they're not meeting that response goal of 12 minutes or less. Now this illustrates the functions and formulas that you could use to do this sort of procedure in Excel. C1 contains the count function. We're assuming that the data values themselves are in cells A2 through A41. C2 is the average function being used to calculate the value for X bar. You take the average of the 40 numbers that are over there in column A. Now it doesn't show anything past row 12. Rows 13 through 41, they're not being illustrated because you'd have to make the font too small. You couldn't read it. Cell C4 is for you to type in whatever the population standard deviation is. Cell C5 is for you to type in the hypothesized value of the mean. Now, cell C7 calculates the standard error of the mean. C4 contains that population standard deviation, and you divide it by the square root of the sample size, and the sample size is up in C1. The test statistic, you take the difference between the sample mean, which is in C2, and the population mean, which is in C5, and divide it by the standard error, which is in C7. But that will give you the computed value of the test statistic. Now that's a z-value, so you can use the standard normal the standard normal probability function, the norm.s.dist. You can use that function in Excel to get you the probability. Now it's going to return the probability that you're less than or equal to the value, and that's precisely what you need for a lower tail p-value. Now if you want the upper tail p-value, all you have to do is subtract that number from 1. And then to get the p-value for a two-tail test, you can use the minimum function. Plug in the cell that contains the lower tail p-value and the one that contains the upper tail p-value, and have it do a minimum on those two, and then just multiply that times 2. The asterisk is the multiplication operator in Excel. And then this slide shows the numbers. We have a sample size of 40. The average function calculates the mean to be 13.25. The 3.2, the 12, they were entered. The standard error of the mean was calculated. The test statistic, the computed value, was 2.47. You can see there's a little bit of a difference here. The 2.47 was rounded off to 2 decimal places, whereas when you do this sort of thing in Excel, it's going to keep a lot of extra decimal places. So you see a little bit of difference in these probability values. I think it was 0.9932 when we looked it up in the table for 2.47. But the number is not exactly 2.47. So when you subtract that 9933 from 1, you get 0.0067. But anyway, it's not that far off. It's still smaller than the 0.05, so it tells you to reject the null. If it was a two-tail test, you just take that upper tail value, which is the smaller of the two, and just double it. Now if you're doing the critical value approach, you have the same initial first 3 steps. You go through there and compute the test statistic, and it was the 2.47. But when you get to step 4, you take the level of significance. Now in this problem, it was an upper tail test. So you put that 0.05 in the upper tail. Now that means that there's a 95% chance that you're below that number. And the 0.95 is what you need to use in the Z table. And that's one of the ones that's right smack dab in the middle. So you get a Z value of 1.645. So your decision rule, this is an upper tail. If that computed value is greater than or equal to the 1.645, the critical value, then you're going to reject the null. And since our computed value is 2.47, it is larger, so we're going to reject the null. So there's sufficient evidence to indicate that Metro EMS, that they're not meeting that response goal of 12 minutes or less. You're going to get the same answer whether you use the critical value approach or whether you use the p-value approach. But I kind of like drawing the picture, and then all I have to do is just look at it and see where the number is. I have a 0.05 level of significance for an upper tail test. So I put the reject part in the upper tail, and I can figure out from that 0.05 what that z-value is that separates the reject part in the upper tail to the right from the do not reject part, which is to the left. And then I can go to the table and get the 1.645. Then all I have to do is compare the 2.47 and say, well, where is it? Is it in the reject area? Is it out there in the tail? Or is it in the do not reject area? Is it closer to the middle? But in this case, it's in the reject area, so we're going to reject the null. Now, the second test statistic that we're going to cover in this presentation is the student's t-distribution. It's for the case where you're testing the mean, but you don't know what the value of sigma is. You can't use the formula that has a sigma in it unless you know what the value is. So we're going to use student's t-distribution. The t-value is x bar minus the mean with the subscript of 0 divided by s over the square root of n. S is the sample standard deviation. We don't know what sigma is, but if you have the sample, you should be able to calculate x bar, and you should be able to calculate s. Now, student's t-distribution, this particular version of it, has n minus 1 degrees of freedom. You just take the sample size minus 1 to have the number that you need when you go to the t-table. It's a different test statistic. P-value approach, critical value approach, it's basically the same thing. It's just with the t, we're going to go to the t-table to get critical values. The p-value approach, when you go to the table, it's not that good. You can come up with a range on the p-value, but I'm going to show you how that part works. I'm also going to show you the Excel part where you can use the t-distribution in Excel, and you get p-values that way. And if you have a statistical package that does p-values, the p-value approach is probably used quite a bit more than critical value approaches. But the rules are the same. You reject the null if your p-value is less than or equal to alpha. You reject the null for a lower tail test if your computed value is to the left of your critical value. If it's an upper tail test, you're going to reject the null if your computed value is larger than your critical value. But it's just basically reject if you're in the tail. Two-tail test, you're going to have two tails. You're going to have a lower tail critical value. You're going to have an upper tail critical value. Those values are determined by taking alpha and cutting it in half. You put half of alpha on one side, half of alpha on the other side. Now, as I mentioned before, when you're using the table, you're not going to be able to get an exact p-value. But you can get, at best, a lower bound and an upper bound. Sometimes you can only get an upper bound. Sometimes you can only get a lower bound. But statistical software, it's pretty easy to come up with a p-value for a t-test. Now, this is a fairly nice example for a t-test. The highway patrol has a stretch of road where the speed limit's 65 miles an hour. Now, as long as people are doing under 65, there's no reason to put up a radar position to try to catch people speeding. They want to use locations to where they've determined that the average speed is above 65. So they're going to set up a radar if they have enough evidence to suggest that people on average are speeding in this area. Is the average speed above 65? But that's going to be their alternate hypothesis. Now, they set up a little test area. They looked at 64 vehicles, probably with their radar guns, and they found out that the sample mean for the 64 was 66.2 miles per hour, and that sample standard deviation was 4.2 miles per hour. Now, we don't have population information here. We just have information for the sample. So we're going to make use of the t-test. We want to use a 0.05 level of significance. So regardless of whether you're doing it with the p-value or whether you're doing it based on the critical value, you set up the null and the alternate. We have an upper tail test. The level of significance is 0.05. Now we can take the sample information, take the x-bar value, 66.2, subtract the mean that's hypothesized, 65, that's up there in the null hypothesis, and divide it by the 4.2, the sample standard deviation, over the square root of the sample size. Now, the t-table that they have in the textbook is accurate to 3 decimal places, so they've rounded this off to 3 decimal places. The t-table that I made available is accurate to 4 decimal places, but you can use 3. I mean, that's fine. So we're coming up with 2.286 for the computed value. Now, if you're using the p-value approach, what you want to do is to find the probability that you're to the right, because this is an upper tail test. Our computed value is 2.286. Now, the t-table, it's broken down by the degrees of freedom. We had a sample size of 64, so we're going to have 63 degrees of freedom. So you want to look in the row with 63 degrees of freedom. The first number in there is 0.8474. 2.286 is to the right of that. So we look at the next number. It's to the right of that. We look at the next number. It's to the right of that. We look at the next number. It's to the right of that. But when we get to the 0.01 column, we're getting to a number that's larger than 2.286. So we found where it is in the table. It's between 1.9983 and 2.3870. So when you look at the probabilities at the top of those two columns, that tells you that for a one-tail test, the p-value has to be between those two. It's got to be larger than 0.01, but it's got to be smaller than 0.025. Now, this is the way you do it for a one-tail test. If this was a two-tail test, then all you'd have to do is to take these two numbers and double them. So for a two-tail test, you would take the 0.01 and double it and get 0.02, and you take the 0.025 and double it and get 0.05. But for a two-tail test, we would determine, based on the numbers in the table, that the p-value is between 0.02 and 0.05. But this particular example was a one-tail test, so we know that the p-value is between 0.01 and 0.025. Now, the level of significance was 0.05, and we determined from the table that the p-value is somewhere between 0.01 and 0.025. No matter where it is in that range, it's smaller than 0.05. So we're going to reject the null. So we have sufficient evidence here that the mean speed of the vehicles at this particular location is greater than 65 miles an hour. And you could say that you're 95% confident about that, or you could say that we've determined this at the 0.05 level of significance. Either way, it'd be fine. Now, this slide shows the functions and the formulas that you can use in Excel for the t-test. In C1, you have the count that's determining what the sample size is. In C2, you have the average function that's figuring out the value of x bar. In C3, you've got the sample standard deviation function that's figuring out what the value of s is. In C5, you just type in the hypothesized value. Here we're testing against 65. Now the standard error of the mean would be that standard deviation up in C3 divided by the square root of the sample size. That's what your denominator is in your test statistic. The test statistic, you take x bar, the sample mean, you subtract what that hypothesized value is for the population mean, which is up in C5, take that difference and then divide it by the standard error, which is in C7. Your degrees of freedom would be your sample size minus 1, and that's being stored in C9. Now the t-distribution function is going to give you the probability to the left of the t-value. The t-value is being calculated in C8, and that's your first argument. But you have to specify the degrees of freedom. Now that number is being calculated in C9. And you want, in this case, you want that cumulative probability. You want the part that's less than or equal to. So you put true as that cumulative argument. But that's going to give you the lower tail p-value, because it's finding the probability before that t-value, to the left of that t-value. If you have an upper tail test, you want the probability to the right of that t-value, so you just subtract that number from 1. You take the probability to the left side and subtract that probability from 1, and you've got the probability for the other side. And if it's a two-tail test, just whichever one of them is smaller, the smaller number in C11 or C12, just multiply that by 2. This slide shows the numbers that are returned by the functions and the formulas in Excel. If you go down to the bottom where you have the p-value for the upper tail test, the value is 0.0128. Because that's smaller than the level of significance, that tells you to reject the null. Now when we looked at the t-table, all we could determine was that the p-value was between 0.01 and 0.025. But here you can get the p-value to pretty much any number of decimal places, up to about maybe 12. There's one of the homework problems, I believe, where they're asking for the p-value for a t-test to maybe 4 decimal places, like it's displaying it here. And you definitely want to use Excel for that problem, because all you can do with the t-table is to come up with a range. Now if you're doing it based on the critical value approach, you're going to go through those steps 1, 2, and 3 just the same. You get the null and the alternate, you figure out the level of significance, and then you calculate the value of the test statistic, and we're coming up with the 2.286, just like we did for the p-value approach. But the difference is you take the 0.05 and you figure out what's the point that separates the reject part from the do not reject part. Now since this is an upper tail test, you're going to put the 0.05 in the upper tail. The degrees of freedom, the sample size is 64, so 64 minus 1 is 63. But you look in the column where you have 0.05, and you look in the row where the degrees of freedom is 63. And the t-value that's in the table, if you look back up at the previous slide where I showed you the table to come up with the p-value, there it's going to be 1.6694 because I put an extra decimal place in it. But you can round it off to 3. You get 1.669. But the rule, you're going to reject the null if the computed value, if it's larger or equal to the 1.669. And since that 2.286 is bigger, we're going to reject the null. So we found evidence, sufficient evidence in this case, at the 0.05 level of significance, that the mean speed of the vehicles at this particular location is greater than 65 miles an hour. But your decision's always going to be the same whether you use the critical value or whether you use the p-value approach. But this slide shows both of them it shows the p-value approach and the critical value approach. The critical value is at 1.669. That's determined by alpha. And your 2.286 is larger, so you're going to reject on an upper tail test. The p-value, if you're using the table, you'll determine that it's between 0.01 and 0.025. But anything that's in that range is smaller than 0.05. So your p-value is smaller, so you're going to reject the null. But either way you look at it, you end up rejecting the null. Alright, the last topic is looking at the proportion. Now once again, you always put the equal to up in the null. We're just going to have a different symbol. We're using the subscript of 0 to indicate the value that's hypothesized, but you can have a lower tail test to where you're trying to show that the proportion is smaller than some value. You can have an upper tail test where you're trying to show that the proportion is larger than some value. The two-tail test just says this is not what it is. The proportion is not this value. This slide shows the formula for the test statistic when you're testing the proportion under the assumption that n times p, where p is the hypothesized value of the population proportion, n times p is at least 5, and n times the complement, 1 minus p, that's at least 5. But that's the rule of thumb that says it's okay to assume that the sample proportion is normally distributed. So if it's normal, you can subtract its mean, which is the population proportion, and you use the value that's hypothesized, and divide it by the standard deviation of the sample proportion. Now the formula that's in the middle there is the formula for the standard deviation of the proportion, or you can call it the standard error of the proportion. Now a really common mistake is that under the square root sign, people will use the sample proportion instead of what's hypothesized. But the null is true when you do the hypothesis test. So under the null, we're assuming the value is p sub 0. So you take p sub 0 times 1 minus p sub 0, divide it by n, and take the square root to get the standard error of the proportion. About the only thing that's different between testing the mean with the z and testing the proportion with the z is the symbol. We're not using the symbol mu, we're using the symbol p. The p-value approach, it's the same rule. Once you figure out what the p-value is, you're going to reject the null if it turns out to be less than or equal to alpha. The p-value is going to be determined by the computed value. You've got a different formula to figure out what that is. But if it's a lower tail test, you're going to take the probability to the left of the computed value. If it's an upper tail test, you're going to take the probability to the right. And if it's a two-tail test, you take 2 times the minimum of those two values. If you're doing the critical value approach for a lower tail test, you take all of alpha and you put it on the left tail. And then you figure out what's the z value, what's that critical value that separates that left tail from the rest of it. And you're going to reject the null if you're out in the tail. All you have to do is compare the computed value to that critical value and see if you're smaller or equal. For an upper tail test, it's just on the other side. You take all of alpha and you put it on the right tail. And then you go to the table and figure out what's the z value that separates that right tail from the rest of it. That's your critical value. If the computed value is that large or larger, if it's out in the tail, then you're going to reject the null. And then for a two-tail test, all you do is take alpha and split it in half, figure out what the two critical values are. You're going to reject if you're in either tail. If it turns out that the computed value is between those two critical values, then you're not going to reject the null. All right, now we have this information from the National Safety Council. For Christmas and New Year's week, they estimate that 500 people are going to be killed and 25,000 injured. That's not really relevant to the question here. They're claiming that 50% of the accidents are caused by drunk driving. That's what their claim is. So under the null, we're assuming that the proportion is 50%. We're going to try to show that that's not right. We're going to try to show that the actual proportion differs from 50%. But they claimed it's 50%. We don't have any reason, the way this problem stated, to try to show that it's more than 50% or it's less than 50%. We're just going to test that claim. They claim it's 50%. Okay, we'll set that up as a null, and then we'll see whether or not our sample data, does it significantly differ from that. So the sample, you've got 120 accidents, 67 of them were caused by drunk driving. So the sample proportion is going to be 67 divided by 120. Now we want to test the claim at the 0.05 level of significance. Now regardless of whether you're doing the p-value approach or the critical value approach, you have the same three steps. First, you determine the hypotheses. There was a claim of 50%. That's what we set up under the null. We're testing that claim. We're going to try to show under the alternative that it's not 50%. There wasn't anything in the problem that suggested that we need to show that it's more than 50%, or that we should try to show that it's less than 50%. There was a claim of 50%, and so we're going to test that claim. Alpha is 0.05. The third step is to calculate the value of the test statistic. So the formula is you take the sample proportion, you subtract the population proportion, what's hypothesized, and then divide it by the standard error of the proportion. Now to calculate that standard error, we have to take the hypothesized value times 1 minus that, so we get the 0.5 times 1 minus 0.5, and then divide that by the sample size, which was 120. That number is the variance. You take the square root of the variance to come up with the standard deviation, which is also referred to as the standard error of the proportion. That was 0.045644. Now don't make the mistake of using the sample proportion for this calculation. In the problem, we're assuming that the population proportion is 0.5, and that's the value that you want to use when you figure out the standard error of the proportion. Now to complete the calculation, we take the sample value, which is calculated by 67 over 120. We subtract the population value, which is hypothesized, the 0.5, and then divide it by the standard error of the proportion, the 0.045644. When we round that off to 2 decimal places, we come up with 1.28, which is the computed value of the test statistic. Now using the p-value approach, we take the computed value, the 1.28, go to the z-table and look up the probability. Now the probability that you're going to get is to the left of 1.28, and that number is 0.8997. Now the probability to the right is what you would use for an upper tail test. So 1 minus that would be the would be 0.1003. And that's the number that you'd multiply by 2 because it's smaller. So you take 2 times 0.1003, and the p-value would be 0.2006. Now you compare the p-value to alpha to make the decision. It's not smaller, so we're not going to reject the null. The rule is you reject the null if the p-value is less than or equal to alpha. But we don't have that case here, so we're not going to reject the null. So the claim, we can't refute the claim. The claim was that 50% of them. Well, the number that we got from the sample wasn't exactly 50%, but it wasn't that far off. Now this slide shows the formulas and functions that you could use in Excel to do this procedure. In C1 you have the count function that's being used to come up with the sample size. We're counting the number of yeses. Were these caused by drunk driving? Either yes they were or no they're not. There's a new function here, the COUNTIF function. You count if it's equal to the yes response. The COUNTIF, the first argument, is a range, and you look at the values in that range of data and you count them if they're equal, in this case, to what's in C2. C2 contains the value yes. So we're just counting the number of yeses in the data set. And then the sample proportion would be the number of yeses divided by the sample size. But that's the 67 divided by the 120. You'd have to type in the hypothesized value. You'd have to type in the 0.5. The standard error, you take the square root, that's the SQRT, you take the square root of the hypothesized value times 1 minus that divided by the sample size. And then the test statistic, you take the difference between the sample proportion and what's hypothesized and then divide that by the standard error. And then once we have that z value, that's in C9, we can figure out what the probability is that you're below that you're to the left of that. We're using the standard normal distribution that's in Excel, the norm.s.dist. But you give it the z value, and then the second argument, we want the cumulative form. We want the probability that you're less than or equal to that. And once you get the lower tail probability value, which is what you have for the p-value for the lower tail, you can just subtract that from 1 to get the upper tail. And then whichever one of them is smaller, either the lower tail value or the upper tail, that's what you multiply times 2 to come up with a two-tail p-value. This problem, we need that two-tail p-value. We need the number that's down there in C13. And this slide shows the numbers. The two-tail p-value is 0.2006. That's larger than the 0.05, the level of significance. So it tells us not to reject the null. Now using the critical value approach, we have to come up with the two critical values. This is a two-tail test. So you take the level of significance and cut it in half, and we get 0.025, which should be a rather familiar figure by now. When you put 0.025 in the upper tail, the z value that you're going to get for your critical value is 1.96. The 0.025 in the lower tail will give you the same number, it's just negative. So we're going to reject the null if the computed value is less than or equal to the negative 1.96, or if the computed value is greater than or equal to a positive 1.96. But it's just basically reject the null if the computed value ends up being in the tail based upon those critical values. Now the 1.28 was not in the tail, so we are not going to reject the null. That claim of 50%, we cannot refute it. We have to accept that claim in this case. This concludes Chapter 9 on hypothesis testing. We've covered lower tail test, upper tail test, two-tail test. We've covered how to do them with the p-value approach. We've covered how to do them with the critical value approach. And we've covered 3 different test statistics. Testing the mean where you know sigma, testing the mean where you don't know sigma, and testing the proportion. Now the next chapter, we're going to look at 2 populations, but we're not going to look at proportion test. We're only going to look at the test of the mean. We'll be comparing the mean of one population to the mean of another population. And there's only 2 cases. Either we know sigma 1 and sigma 2, we know the population standard deviations for each one, or we don't. If we know them, we're going to use a z. If we don't know them, we're going to use the student's t-distribution. But it should be reasonably familiar. It's just longer. There's just more calculations to it. But we'll get into that next time.